The next topic we are talking about is trig substitutions. Trig substitutions. It's a different type of substitutions. Trig substitutions, a different type of substitutions. Okay. Uh, I will let you take a look at the handouts first. So basically, I want to show you for what type of the integrals we are going to use trig substitutions. Again, so download handout number 4. On the screen, you have the handout. Okay. Now look at all the questions in question 2. All the integrals in question 2. Okay. For all the integrals in question 2, you have a radical involved. Okay. In most cases, you have a square root involved in the integral. In this case, we are using trig substitutions. So basically, we want to do something to get rid of the radicals. Okay, so basically the trig substitutions are going to be used to handle three types of the radicals. Actually, all of them are square roots. One is if a integral in the function, the integrand, you have a radical in that form, something like a squared minus x squared. So now let's say in question 2a, you have a radical square root of 4 minus x squared, right? Square root of 2 squared minus x squared. You just imagine a value is 2. In this case, we use a substitution like this. We set x to be a sine of theta. Okay, sine of theta. Theta is I said it's a different type of the substitution. In the substitution we learned before, the substitution rule. Okay, we set u to be a function of x. You remember that? In this case, we set x to be a function of another variable, theta. Okay, so you're going to see why, how it works. The reason it will work, so because we call it the trig substitutions, the reason the whole thing will work is because of some trig identities. So how about we'll do one of the questions first, so you will know what I mean. Okay. We'll work on a simple question first. Okay. We're going to do question 2a first. A simple question showing you how the trig substitution will work. Actually, we learned how to evaluate an integral like that in Math 1.1, but now we are going to use the new technique, trig substitution. In the future, whenever you see a radical in that form, we can use a trig substitution to work on it. Okay. Now the solution to that. Again, the radical is in the form of a squared minus x squared. In this particular case, a value is 2, right? So we have the form of, so now let's say 2 squared minus x squared. Again, a value is 2 in this particular question. If you look at the table in here, the substitution we need is let x be 2 sine of theta. Theta is a new variable. I said theta, so this thing is called theta. Okay. Another Greek letter. I will show you how the thing will work. How we want to get rid of the radical. We want to get rid of square root. I will let you see how the thing will get rid of the radical. Okay. We let x be sine of theta. So what we will do is to use the substitution to convert the integral to a new integral of theta. Everything is going to be in terms of theta. Okay. The main thing is how to get rid of the radical. We'll work on the radical first. Okay. And then square root the radical. We want to get rid of the radical. In the new integral, you are going to see there will be no radical anymore. Okay. 4 minus x squared equals. And by the way, in the substitution, there's a restriction on theta. There's a restriction on theta. Theta is in general in between negative half pi and half pi, but you really do not have to memorize that. You just remember there's a range of theta. If you need it, you go back to the range to remember that. Okay. I will tell you how that condition is used. Okay. If you want to remember, this is actually the range for inverse sine of theta. You remember the range for inverse sine is defined. Again, this is the range for inverse sine. I will tell you how that condition works. I'm trying to say in the solution you do not have to mention the restriction on theta. Okay. We're going to see how to get rid of the radical now. Okay. So 4 minus x squared will become everything is in the new integral. Everything is going to be in terms of a new variable of theta. Okay. 4 minus x squared will become 4 minus. Sorry, I think I forgot the coefficient already. Sorry, I just took a nap. I hope I woke up now. I kind of woke up now. Okay. X equals 2 sine of theta. In general, in the table, you look at the table. The substitution we need is x equals a sine of theta. In this particular case, a value is 2, so that's why I said x to be 2 sine of theta. Okay. 4 minus 2 x squared will be 4x squared. Sorry. Four sine of theta, the whole thing squared. Write squared in here, so do not write squared here. Okay, we mean sine of theta, the whole thing squared. We are going to see how to get rid of the radical, how the thing will work. Okay. So this thing is equal to square root of, you have a common factor of 4, and then you take you leave 4 out of the radical notation. Square root of 4 is 2. We can leave 2 out of the radical notation, right? Inside the radical, under the radical, we have only 1 minus sine of theta, the whole thing squared. Okay. Now we're going to see how to get rid of the radical. Okay, using the trig identity. The trig identity, you remember 1 minus sine of theta, the whole thing squared. It's cos of theta squared, right? Cos of theta, the whole thing squared. We have seen the trig identity over and over. In the table, I even told you why we can get rid of the identity, get rid of the radical using identity. The trig identity we use to get rid of the radical is that. Okay. Under the radical, you have 1 minus sine of theta, the whole thing squared. So yeah, that's why. Now, for the stuff under radical, I will replace that with cos of theta, the whole thing squared. Okay. In general, so do you want to recall for any number? So now let's say c. If you have c squared and then you take square root. So in general, what's the answer to that? The answer is now c. The answer is actually the absolute value of c. C itself, it could be negative. Okay. That's where the restriction on theta will work. Recall a little bit from your high school math. Okay, when theta is in between negative half pi and half pi, cos of theta is always positive. Again, I want to repeat, when theta is in between negative half pi and half pi, cos of theta is always positive. That's why cos of theta, the whole thing squared. So because cos of theta is always positive, you take square root of cos of theta, the whole thing squared. You have 2 cos of theta. Okay. You see the radical is gone. So that's the whole idea. In the new integral, you see the radical on denominator, the square root is gone, right? And then of course we need to convert everything in terms of a new variable theta, including the dx. We still have to compute dx. Okay. Actually, in most cases you do dx first, but I was trying to concentrate on how to get rid of the radical. Now let's get dx in here. Again, we want to convert everything in terms of a new variable theta. So this is a different type of the substitution. I think when I did my university, we just call it type 2 substitution, but I don't think anybody says it that way anymore. Again, you just remember it's a different type. In old days, the substitution we use is to set u to be a function of x. So in this time, we set x to be a function of another variable. In this case, we use theta. So because theta is a commonly used notation for angles. Okay. Still, you have to compute dx. The relation between x and theta is here. To compute dx, you do differential. Okay. So don't be confused about the differentiate, the derivative and the antiderivative. So here we need the derivative of the function. So we have 2 times the derivative of sine of theta is cos of theta. Okay, cos of theta. Now here dx, it means the differential of x. So do not forget to multiply d theta. It's part of the differential notation. So do not forget d theta. Okay, I have seen many people forgot dx, d theta, d whatever thing on the assignment. So not 1, not 2, many. Okay, now we are ready to convert the whole integral, the integral entirely in terms of a new variable theta. Okay, yeah, probably I think it's still in the memory. I'm going to copy that. The given integral, now we are going to rewrite everything in terms of theta. Now you look at here. Square root of 4 minus x squared, it becomes 2 cos of theta. It's on denominator, right? On denominator, you have cos of theta. On the numerator, originally you had 1. Now dx is 2 cos of theta d theta. You just copy this dx is 2 cos of theta d theta. Right. I know the integral is easy, so but the key point in here, the main thing in here, I want you to see. After the conversion, after you get everything in terms of theta, the radical notation is gone. The square root is gone. So that's the main thing. Yeah, that's the main idea, right? And for this one, so because it's simple, we are going to complete the solution. Okay. Cos of theta and cos of theta is cancelled. And then you take out the constant of 2. So you are trying to compute 2 times 1 the integrand in this case is 1, I do not have to write 1, I just write b theta. Okay. And then the answer to that, the new integral is integral of theta. Antiderivative of 1 is not x in this case. Antiderivative of 1 is theta. So because the integral is an integral of theta. So that makes sense? So you have 2 antiderivative of 1 theta, okay, 2 theta and then plus c. So that makes sense? But we are not done yet. We are not done yet. So any question? We are not done yet. The
Excuse me, sir.
Sure.
As the 4 minus x square, the whole square is equal to 2 cos theta. So why you just write the cos theta?
I took out a common factor of 4. And then 4 out of the radical, it becomes 2. Right?
Yeah, okay. So when we finally compute, then you just write the cos theta. 2 cos theta upon just cos theta. So there should be 2 cos theta, right?
So which line are we talking about?
The last line. The
last?
final, when we get the answer.
Yeah. So give me a little moment. Yeah, you're right. So you're right. I think you're right. Sorry about that. Now for this one, now let me try again. Okay. I think for you're right. Yeah, I think I missed the 2 in here. So that's what you meant, I guess. I missed the 2 in here. So the entire radical is 2 cos of theta. Okay, so thank you for telling me that. I'm sorry about that. I think after removing the factor of 2, everything is right. Right. Still, so thank you. Still, that's not the final answer. For the final answer, original integral is integral of x. You need to write the final answer as a function of x. So yeah, so this time the final answer in some cases it's a little bit weird, but in this case it's simple. We always use the relation between x and theta when we do the substitution. The substitution is a relation between x and theta, right? So the final answer, we want to write the final answer as a function of x. Anybody want to tell me how to write the final answer as a function of x? So maybe I'm going to add a new line in here. So sine of theta is equal to half of x, right? So this means, how do you write theta in terms of x? Theta is equal to, if sine of theta is half of x, how do you represent theta? Theta is
arc sine x by 2.
Inverse sine. So inverse sine of half of x, right? Again, the final answer, originally the integral was a function of x. It's an integral of x. The final answer, it should be a function of x and then plus c. Okay. So the final answer is inverse sine of half of x and then plus c. Okay. That's the complete solution to the question. Again, a simple question trying to show you the radical, how to get rid of the radical, how the substitution works. You see how we use the trig identity, right? Actually, for most of the questions, we're going to do the questions in 2 rounds, using 2 rounds. We're going to do the questions in 2 rounds, okay? The first round is to use a trig substitution to get rid of the radical, get rid of the radicals if there are more than one radicals. Okay. The second round we evaluate the integral. in many cases, the transformed integral, I mean the integral in terms of the new variable theta, in many cases is a little harder to evaluate. You need to recall many other techniques. But the main thing in the section is to make a trig substitution to get rid of the radical. So that's the main thing. Okay. So, but before that, I'm going to do question B. In question B, I'm not going to finish question B. Okay. But my intention on question B is to show you some alternative forms. By alternative forms, you see the radicals are very similar in question A and question B, right? So, but in question B, there could be a coefficient of x. If you want, I can add some more lines in the table. I will add more lines in the table, okay? So maybe very similar to the first case. If you have a radical, it's something like this: a squared minus b squared and then times x squared. In this case, we use a trig substitution. I just show you the trig substitution. Okay, the trig substitution to get rid of the radical is going to be, you guys are smart, so anybody want to guess? It's some number times sine of theta. But if you have a b squared before x squared, the coefficient here is going to be a little different. The coefficient before sine of theta is a little different. Okay. The substitution we need is a over b sine of theta. I will show you what I mean using question 2. But for question 2, I only perform a substitution, only use a substitution to get rid of the radical. Okay. It always asks me to edit picture. I'm not editing picture. We only do the first round. I'm not going to evaluate the complete integral. I only do a substitution to get rid of the radical. After getting rid of the radical, then I'm done. Okay. Anybody want to tell me the substitution we need here? X equals, you know it's going to be something sine of theta. So just tell me the numbers before. So just tell me the coefficients. Anybody want to tell me the coefficient? The number before sine of theta, so that we can get rid of the radical.
3?
No, still you need 2. I think 2 over 3. 2 over 3. 3 is close. 2 over 3. Okay. 2 is coming from you treat 4 as 2 squared. You treat 3 as no, you treat 9 as 3 squared. And then you just put 3 on denominator. I will show you how the thing will work. Okay. In general, after making the substitution, the first thing we do is to compute dx. In most cases, yeah, that's the first thing we do. Okay. So we have 2 over 3. Sorry, I was trying to write 2 over 3 sine cos of theta. We differentiate sine of theta, we have cos of theta. Again, for the people who took the course a long time ago, review what we mean by the derivative, what we mean by antiderivative, so don't be confused. Okay. Here we need the derivative of sine of theta. The derivative of sine is cos. In most cases, that is the first thing we do. Okay, and then you do something to get rid of the radical. wherever you see the radical, you copy the radical. Okay, copy the radical. The radical is 4 minus 9 x squared. At this time, I'm going to be a little careful. Okay, you have square root. Wherever you see x, you replace x with 2 over 3 sine of theta. So you have 4 minus 2, 9 times, right? 9 times. I'm going to do it a little bit slower. X squared will become 2 squared, so which is 4, right? Over 9, and then sine of theta, the whole thing squared. So do you see how this thing will work? The 9 is cancelled, and then you take out 4. The whole thing will be 1 minus sine of theta, the whole thing squared. That's where we can use a trig identity to get rid of the radical. Right. I will keep on writing. Nine is cancelled. So this time I'm going to do this a little bit slower, so just in case some of you guys are confused. I'll cancel out 9 first, and then you take 4 out of the 2 terms. You take out a common factor of 4, and then you have 1 minus sine of theta, the whole thing squared. Right. Still we have and then square root of 4 is equal to 2, and then 2 times square root of, now for the stuff inside the brackets, 1 minus sine of theta, the whole thing squared. It will become cos of theta, the whole thing squared, right? Again, in most cases, you do not have to write the restriction on theta, but when theta is in between negative half pi and half pi, cos of theta is always positive. That's why you do not need the absolute value of cos of theta. So you just have 2 cos of theta. You see the radical is gone. That's actually the amendment step. The amendment thing. So the given integral now is very similar to the other one. Okay, it's very similar to the other one. The given integral now is the same as before. I do not want to see two variables in one integral. Now everything is going to be in terms of theta. Okay. The denominator, the radical, it becomes, this time I'll be careful. Okay. The radical becomes 2 cos of theta. Right. And the numerator is dx. Now dx, it becomes 2 over 3 cos of theta, and then d theta, right? You see in the new integral, new integral of theta, the radical is gone. I will stop here. If you want to evaluate, I know the rest of the step is simple, but now I'm done what is required in the first requirement. If you look at the handout, if you read the question, now question A, for each of the following integrals, the first thing you do is to use a trig substitution to transform the integral and eliminate the radicals. I'm done that. Okay, I'm done the first round. The second round, the second thing we do is to evaluate. Again, in many cases, the evaluation of the new integral is not too simple. In many cases, so you're going to see. Okay, but the main thing is the first. The main new thing. The new thing is actually the first thing we do. How to use a trig substitution to get rid of the radicals. Okay. For the midterm or some test or the assignment even probably, for some questions I just ask you to do the first step. The wording of the question is kind of that. Use a trig substitution to transform the integral, okay, and eliminate the radicals. So that's probably the wording I'm going to use. By that we mean after you get rid of the radicals, after you convert the integral to a new integral of theta without radicals, then you're done. Yeah, I was trying to do this. For the table, I'm going to add more lines for other cases. Now look at the second case. In the second case, if you have a radical in the form of actually all the trig identities, I think I told you all the trig identities when we learn the trig integrals. You'll remember the techniques. Okay, the first new technique we did was the integration by parts. The second technique we learned is trig integrals, in which we learned all the identities. Right. The second line the second new line corresponding to the second line in here, I want to add a new case in here. Okay, if you have a radical in the form like a squared and then plus b squared and then times x squared, and then the trig substitution we need is, you want to guess? Now look at the second line in here. It's very similar to that. X equals a over b tan of theta, in which you need to use a trig identity of that to get rid of the radical. Okay. 1 plus tan of theta the whole thing squared is secant of theta the whole thing squared. The third case, corresponding to the third line in the table, I want to add one more line. Okay. If you see a radical something like b squared, now let's say minus b squared times x squared minus a squared. So very similarly, the substitution we need is to let x be I think a over b the times secant of theta the whole thing squared. The restrictions on theta are the same as the restrictions on the table. Okay. Okay, now we'll look at the handout to see the second case. I hope I have a question about the second case. I think question F is a question in the second case. So this time I'm going to let you see a question which could be a little bit more complicated. Actually, you see this time you have a definite integral. The idea is the same. In the integral, you'll see you have a square root of a function in the form of the second case. The second case is x squared plus a number squared, right? In the question you have so don't worry about the cube. The cube thing is essentially I'm trying to say I'm just talking about the denominator, so maybe I'm going to write the whole thing. Square root of x squared and then plus 1, the whole thing cubed, is the same thing as square root of x plus 1 and then that thing cubed. Essentially, the identity, the two functions are the same thing. You see, I'm trying to say the radical is essentially square root of x squared and then plus 1 squared, so which is in the same form as the radical in the second line, right, in the table. If you haven't, I did not give you a chance to copy. Now take a picture of this page, of this slide. Take a picture of the slide. Actually, this thing is on the course manual. You do not have to copy. If you downloaded the course manual, you can look at it. You can open the course manual actually. If you see the radical that way, now you see the substitution we need. Okay. Anybody want to write the substitution we need? So please, anybody want to write the substitution we need to get rid of the radical? We let x be some theta. I'm looking at a trig substitution. A substitution. The function is going to be some theta. Now look at the table. The substitution is going to be a trig function, a number times a trig function actually. Now the radical is in the form of square root of x squared plus 1. Now let's go back to this thing. Now look at the second line. In here we have square root of 1 plus x squared. Yeah, something like that. But what are a and b? A and b are both 1s. It's just tan of theta. Okay. We let x be tan of theta. That is the substitution we need. If you do not fully get this, now look at the second line. In the second line, for the particular question, we had square root of, let's say, 1 squared and then plus x squared. The same thing as x squared plus 1, right? This is a particular case that a value is equal to 1. So do you see a value is 1? When a value is 1, the substitution you need is x times a times tan of theta, x times tan of theta, because a value is 1. That is the substitution we need. Okay. Of course, there's a restriction on theta. In most cases, we do not write it down in the solution. It's kind of hard to remember that. I will just do something to get rid of the radical, and then we're done the first round, so we're done the main thing, the menu thing, I mean. After set x to be a trig function of theta, the next thing we do is to compute dx. Okay. The same idea as before. We just want to rewrite the integral entirely in terms of the new variable theta. Okay. So dx, this time you differentiate tan of theta. You have secant squared of theta, secant of theta, the whole thing squared. Do not forget d theta. D theta is part of the differential notation. So later on in the new integral, you have to have d theta. Right? All right. And then the main thing is how we can get rid of the radical. Okay. I'm going to rewrite the radical in slightly different form. The given radical, so now let's say x squared and then plus 1, the whole thing to the power of 3. I told you earlier it's the same thing as square root of x squared plus 1. Now the whole thing to the power of 3. They're the same thing. Okay. Now I'm going to replace x with tan of theta to see what's going on. You are going to see where we use the identity. Okay. So we have wherever I see x, I replace x with tan of theta. So you have tan of theta, the whole thing squared, and then plus 1, and then the whole thing cubed, right? For these commonly used trig identities, I really do not always want you to look at the formula sheets or whatever you call it. You really need to memorize all these identities. Okay, wherever you see the identities, then I want you to be able to immediately use the identities. So what do you have? You have square root of tan of theta, the whole thing squared, and then plus 1. So what is that? Using the trig identity, you see as secant of theta, the whole thing squared, right? So do not forget the whole thing cubed. Now we are almost ready to get get rid of the radical. Okay. When theta is in between negative half pi and half pi, I was talking about the restriction on theta. When we make the substitution, you see if the substitution is a tan of theta, the restriction on theta is in between negative half pi and half pi. So that's what I said, right? I believe when theta is in between negative half pi and half pi, secant of theta is always positive. I'm trying to say square root of secant of theta, the whole thing squared, now becomes secant of theta. It's kind of 2 squared, and then you take square root. It's the same thing as 2, right? It's comparable to that. Okay. So do not forget the cubed. This cubed is coming from that 3. Okay. Now we are ready to transform the integral. Okay. Actually, for a definite integral, you need to do some extra steps. Now look at the integral. This lower limit of 0 is the lower limit, that's x value. Okay. The upper limit, the square root of 3, is x value. We also have to convert these values to theta values. Okay. Again, for the definite integral, you have one additional step. You have to get theta values corresponding to x value of 0 and the x value of square root of 3. Okay. Maybe moreover, x value of 0, we're going to determine theta value. Okay. And the x value of square root of 3, we're going to get the theta value for x value of 0 and root 3. Using the relation between x and theta, the relations here. Okay. Of course, you need to take the theta value in the range of inverse tan of theta. By that we mean you take theta value to be in between negative half pi and half pi. In this case, it's simple. Okay. To put it simply, the relation between x and theta is here. The substitution. Okay. To get theta, you think tan of what angle in radian is equal to 0? Tan of what angle in radian is equal to 0? Anybody want to tell me very quickly? Tan of what angle in radian is equal to 0? 0. Okay. Tan of 0 is 0. In Math 101, I give you the unit circle. But here, I believe it's not too hard to get this. Anybody want to tell me tan of what angle in radian is equal to square root of 3? Tan of what?
3.
I'm looking for angle. Pi over something. Pi over
5/3.
pi over 6?
No, 3.
I think pi over 3. Yeah, pi over 3 is right. Pi over 3 is right. Sure, thank you. It's pi over 3. Okay. If you are confused, so look at the unit circle I gave you in Math 101. You open any assignment, the unit circle I believe is on the instruction page. So do you remember? Again, the reason here is tan of pi over 3 is equal to square root of 3. Or alternatively, you draw a triangle, something like this. I think you have one leg is 1, the hypotenuse is 2. This leg is square root of 3. Tan is opposite over adjacent, so that's pi over 3, right? Whatever way you want to use, theta value is pi over 3. Again, for definite integral, you need to get the theta values for x value of 0 at root 3. Okay. Again, I'm not going to complete the solution to this one. Okay, but I will convert the integral to a new integral of theta. If we have time, we'll go back to complete the solution. Okay, now the given integral. I think now we are ready to write everything in terms of the new variable theta. After converting the integral to a new integral of theta, the lower limit will be the theta value of 0. That's theta value of 0. Okay, and corresponding to x value of root 3, you have theta value of pi over 3. Right. At this point, I think we are ready to convert everything to a new integral of theta. Okay. The radical becomes. I mean, the denominator now becomes secant of theta, the whole thing cubed. Now look at the denominator here. We computed the denominator, right? And the dx now becomes secant of theta, the whole thing squared. So do not forget d theta. Okay. The only thing we have to include in here is x cubed. You replace x with tan of theta, and x cubed will be tan of theta, the whole thing cubed. I'm done question A. So do you see in question A, I wanted you to use a trig substitution to transform the integral and get rid of the radical? I'm done, right? The radical is gone. In the new integral of theta, the radical is gone. Actually, for this one, it's not too hard to evaluate. Okay? So if we have time, we'll go back to this. Okay, but I want to concentrate on the main thing first. I want to concentrate on how to make the substitution to get rid of the radical first. Any questions about this? On the midterm or this assignment, I'm going to for some questions, I just want you to get rid of the radicals to use a trig substitution to get rid of the radicals. Does a question showing you how to use the second line in the table? I mean the second line in that table. Okay, how to get rid of the radical in that form, and also I showed you how to evaluate a definite integral using the substitution. And by the way, this integral has been transformed to a new integral of theta, including the lower limit and upper limit. If you evaluate, if you want to finish, do not go back to x. Okay, you just evaluate the new integral of theta, plug in the using the fundamental to evaluate a new integral of theta. Okay, so I'm trying to say do not go back to x, because the final answer of a definite integral is a number. Okay, if you don't have any questions, I will see if we can. Now question D. So question D is showing you how to. Question D is in the nature of using the third trig identity to get rid of the radical. I will go over question D now. Okay. I think you got the idea. I'm going to run a little bit. Anybody want to tell me the substitution you need? So please, now look at your phone. Look at your phone. For the table, in the table we have for all kinds of the radicals, I gave you the trig substitution you need. Okay. Anybody want to tell me the trig substitution you need for this one? If you have the radical in the form of x squared minus 2 squared, I said 2 squared is 4, right? 2 times, so please, so tell me 2 times what trig function we need? What trig function do we need, please? 2 times, so please. Yeah, secant of theta. I think that's right. Secant of theta, 2 times secant of theta. In the substitution, there's no minus 1 in here. Okay. After getting the substitution, in the substitution there's no minus 1 in here. Everything is in the table. So maybe together with the 3 new lines, you'll have almost all the cases. Actually, there's only one extra case. I'm going to show you the extra case later. Okay. But okay, 2 secant of theta. Okay. We'll see how this thing will be able to get rid of the radical. Follow the routine. The next thing we need is to compute dx. dx is you differentiate 2 secant of theta, right? So you have 2 times the derivative of secant is secant tan. Okay, 2 times secant of theta and then times tan of theta. Again, so do not forget dx. That's one thing. The other thing, you could do it within the integral, but I always suggest people to handle the radical separately. So you don't be confused. You are not going to be confused, I mean. So you have x squared minus 4. Wherever you see x squared, you replace wherever you see x, you replace x with 2 secant of theta. Okay. So you have square root 4 secant of theta the whole thing squared minus 4. You'll see how the trig identity will work. You take out a common factor of 4 from these two terms, and then you leave 4 out of the radical notation. So you have 2, right? And then you have secant of theta the whole thing squared and then minus 1. You see, under the radical you can use a trig identity now. So that's, you see how the trig identity will work to get rid of the radical, right? I think, okay, you have 2 times secant of theta the whole thing squared minus 1. Now look at the table again, the trig identity. Secant of theta the whole thing squared minus 1 is tan of theta. Tan of theta, the whole thing squared. I meant tan of theta, the whole thing squared. Okay. And when theta is in under the restriction of theta, whatever the restriction, tan of theta is positive. That's why you have 2 times tan of theta, right? So we're kind of done the main thing. Okay. Now the given integral, now we're ready to get rid of the radical in the new integral. To get rid of the radical in the new integral. I think I said it right. Now the denominator containing the radical, it becomes 2 tan of theta. dx, you see dx in here. dx, it becomes 2 secant of theta and then tan of theta. And then dx, d theta. I think Chad reminded me the, sorry. Now I know what you mean. D theta, of course. Is good enough? D theta. X cubed, wherever you see x, you replace x with 2 secant of theta. Now x cubed, it will become 8. 8 is 2 cubed, right? And the secant of theta, the whole thing cubed. Do I have this right? I think I got it right. Okay. We just use a trig substitution to eliminate the radical, then we're done. Okay. You do not even have to simplify. As long as I don't see the radicals, then you're done. Okay. I think this integral is not too hard to evaluate. That's probably one of the questions on your assignment. In the assignment, I want you to do the complete solution to evaluate. So maybe I'm going to give you some more hint. I will give you more steps. Okay. The rest of the thing is okay. I want to stop for now for this one. Okay. Later on, I will give you some more questions to show you the meaning. I think we have seen all the three cases, right? You have seen a radical like that, a radical like that, a radical like that. Okay. You see on denominator, essentially you have a radical. I will show you what I mean. Okay. In this class, we just concentrate on how to get rid of the radicals. I think on Monday I'm going to complete the solution to some of the questions at least. Okay, now the denominator, I only rewrite the denominator. Okay, the denominator is essentially a radical. The denominator is x squared plus 6x, right? The whole thing to the power of 3 over 2. If you convert the thing to a radical, essentially you have a square root of x squared plus 6x. Now the whole thing to the power of 3. This time I'm writing 3 in there. You see you have a radical, but the radical is not in any of the form in the table, right? What do we do? Under the radical you have a quadratic function including 6x. So this is where we need complete square. We need to complete square. I think we have seen complete square is useful in many contests, right? Curve sketching, many cases. Okay, I will show you how to complete square. Okay. So maybe I'm going to write the complete square thing on scratch paper. You just imagine on top you have the scratch paper. Okay, you have x squared plus 6x. Again, by completing square, we mean to rewrite the quadratic function in the following form: a number a times x plus or minus b, another number, the whole thing squared. Inside the brackets, you have a perfect square, and then plus or minus c. If you can, actually any quadratic function can be rewritten in that form. That form is called complete square. Actually, the whole procedure is called complete square. Okay, you have x squared plus 6x. We want to add a number to make the first three terms, the underlined three terms, a perfect square. Anybody want to tell me this number? I told you before how to get the number. The number you need is always half of the coefficient of x, the whole thing squared. Coefficient of x is 6. Half of 6 is 3. 3 squared is 9. That is the number we need. I want to repeat. The number you need in here, after making the coefficient of x1, the number you need in here is always half of the coefficient of x, the whole thing squared. Half of 6 is 3. 3 squared is 9. That's how I get this 9. Okay. You plus 9, you have to minus 9 in order the equation is valid. Okay. Now we're almost done this. So this thing is equal to, the first three terms will become x plus 3, the whole thing squared. Right. If you are confused, you multiply that out. Minus 9. Right. I'm trying to say the denominator in the integral, the denominator of the integrand, I mean, okay, now can be rewritten as a square root of something the whole thing squared, something the whole thing cubed. Okay. The function under the radical can be rewritten as x plus 3, the whole thing squared, minus 9 now. Okay. You know, in high school you learned complete square, but you don't know why you do that. In this course, you know, it's used all over places, right? Sorry, I forgot the whole thing cubed. Now you have the whole thing cubed, right? At this point, you can see the substitution you need. Now look at your phone again. Now look at your phone for the table. You just treat x plus 3 as x in the table. Now anybody want to tell me the substitution you need? The question is in the nature that you need to do a little bit more work before seeing the substitution. A little more work is complete square. So please, anybody want to tell me the substitution you need? You treat x plus 3 as x. You set x plus 3 to be? Yes, 3 times. No, sine of theta is not good.
I meant tan, sorry.
Yeah, tan. Yeah, sorry, tan is not good. It's not too good either. If you have x squared plus a number squared, I think you have tan. So this is the case you have secant squared, secant of theta. I mean. So that makes sense. Sorry, my eyes are getting bad. You know, tan. Actually, we need secant of theta. Okay. Essentially, so this means it's the same thing as x equals, let's say, secant of theta minus 3, right? And then we follow the routine, okay? We follow the routine, and then we compute dx.
This is only secant theta or 3 secant theta?
3 secant of theta. Yeah, sorry about that. 3 secant of theta. So you're right. Sorry about that. 3 secant of theta. You're right. You have, and then we follow the routine to compute dx, right? The differential of x. I think we have 3 times secant of theta and then times tan of theta. The derivative of secant of theta and then times d theta. I think I got the differential right. After that, we compute the whole radical. Okay. Now the whole radical in the first step. Okay. Okay, I copied everything. No, I did not. I did not select everything. Okay. I'll try again. Yay. I got everything. Okay, now the whole thing under the radical, is equal to, we'll just go from here, okay? Something cubed. Under the radical, you have x plus 3 is equal to 3 secant of theta. Wherever you see x plus 3, you replace x plus 3 with 3 secant of theta. So you have 9 secant of theta, the whole thing squared, minus 9. And then you take 9 out of the radical. You have 3 square root of secant of theta squared minus 1. So you have 3 square root of trig identity you need to use is tan of theta, secant of theta the whole thing squared minus 1 is tan of theta, right? So you have tan of theta the whole thing squared. You just have 3 tan of theta. I think I forgot cubed. I know some of you guys are trying to tell me that. I forgot this cubed. I should include that thing cubed. Now the whole thing should be 27. Yeah. Can I just suppose the whole thing cubed here? Is the whole thing cubed of that? Now it's 27 times tan of theta. The whole thing cubed. Do I have it right? 27 is coming from 3 cubed. 3 cubed is 27. Okay. Okay, now at this point we are ready to convert the integral to a new integral of theta. Okay. I still want to include everything on one screen. I will just go from here. You go back to the first line. I'm telling you the answer. Okay. The answer now, I think you just plug everything in. You should be okay. Now dx. So what's the numerator? Dx is 3 times secant of theta and then times tan of theta d theta. That is the numerator. And then the denominator you have 27 tan of theta, the whole thing cubed. Do I miss something? I think I got everything. For this one, we got rid of the radical, right? We'll stop here. Again, so today we only concentrate on how to eliminate the radicals. On Monday, I'm going to do a few integrals. I'm going to complete the solution to a few integrals, okay? To give you the complete solution. Yeah, probably we have seen all the cases. So temporarily, don't worry about question 1 yet. Okay. Question 3. Okay, we'll go back to question 1. Actually, so question 1 is kind of useful when we go back to x. In some cases, the new integral is a new integral of theta. After evaluating the integral of theta, you need to go back to the original variable x. If you know how to do question 1, it will help you to go back to original variable in many cases. I will show you how to do question 1. Okay. You are going to have a new assignment. I was trying to save a little time to make some comments, but I think I still have time to talk about this before making some comments on the assignment. Okay, secant of theta is equal to 3. I'm looking for sine of theta. Now let's concentrate on the first part first, the underlined part. Again, we're not doing trigonometry, so this thing will be useful when evaluating an integral using a trig substitution. Okay. Actually, the question is easy. You just need to know SOHCAHTOA thing. Okay. Now let's say sine is opposite over hypotenuse, right? Cos is adjacent over hypotenuse. Tan is opposite over adjacent, and secant is 1 over cos. Cosecant is 1 over sine. As long as you know this, then you should be okay. we concentrate on the underline part. Okay. All we need is to use a triangle. Okay. Secant of theta is 1 over cos. Okay, so maybe I will make the thing a little better, a little easier to understand. Okay. If secant of theta is equal to 3, now we are going to get cos first. Okay, so because secant is 1 over cos, the cos of theta is equal to 1/3. So that makes sense. If you want, I can write the identity for you. Okay, secant of theta is always 1 over cos of theta. Right. At this point, you can form a triangle. If cos of theta is 1/3, you make a triangle, so something like this. Cos of theta is adjacent over hypotenuse, right? Adjacent over hypotenuse. I was trying to make this one a right triangle. I mean, okay. It may not be too proportional, but cos of theta is adjacent over hypotenuse. If that angle is theta, adjacent is that, right? Hypotenuse is that. Now you look at the mouse cursor. If that angle is theta, relative to the angle of theta, adjacent is that line segment. I'm not going to label the points. Hypotenuse is that line segment, right? Now cos of theta is 1 over 3. In the triangle you want to make adjacent 1. You want to make the hypotenuse 3. And then you can solve for opposite. So what's opposite? What is the opposite, please? What is the opposite? In a triangle, 2 legs, the sum of the squares of 2 legs is equal to the hypotenuse square. A square root of something. I think it's square root of 9.
It's a square root of 10.
Yeah. Square root of 3 squared minus 1 squared. Is that right? I think square root of 8. Is that right? I think square root of 8. So which is the same thing as 2 square root of 2. I hope I got this right. But why I don't remember these numbers. Okay, I'm trying to show you how. Okay, square root of 8 is equal to square root of 2 times 4, and then you leave 4 out of the radical, you have 2 square root of 2. That's how I got this. Do I have this right? Why? I don't remember these numbers. I think I have this right. Okay. After you have opposite, after you have the opposite, in the question we are looking for sine of theta. So sine of theta. So tell me sine of theta, please. Sine of theta is opposite over hypotenuse. So it's 2 square root of 2 over 3 opposite relative to angle of theta. Yeah, we're using that. It's called Pythagorean theorem. So we're done the first part of the question, right? I'm going to work on the second part. It's true for any right triangle. The formula, Chad, you told me you wrote down is true for any right triangle. Okay. The second part of the question is if tan of theta is 1/4. You know what triangle you need. Okay. You draw a triangle something like this. You make a a right triangle, you draw a right triangle in which the opposite is 1. So because tan is opposite over adjacent, you make the opposite 1. You make adjacent 4. And then you get the hypotenuse. What is the hypotenuse? Square root of 17, I believe. 17 is coming from 4 squared and then plus 1 squared. That's the angle theta, right? And then whatever thing you are going to get, you want to get cos of theta, right? Cos of theta is equal to, according to the definition, cos of theta is defined as adjacent over hypotenuse. Adjacent this time is 4. Hypotenuse is square root of 17. That's how you get cos of theta. It's just SOHCAHTOA thing. Using
Sir, why, when you were solving for the square root of 17, you said you went 4 squared plus 1 squared, which equals the square root of 17. But when you were solving for the opposite of the first section here, you did 3 squared minus 1. Shouldn't it be 3 squared plus 1 then?
no. In the first question, 3 is the hypotenuse. In the second question, 1 and 4 are 2 legs. Hypotenuse is longer. Okay. It's something like this. In any triangle, if that leg is A, that leg is B, so that leg is C. In any right triangle, it's always true that C squared, the hypotenuse squared, is equal to A squared and then plus B squared. It's the same.
Sorry, I understand.
Okay. It's the same thing as A squared is equal to C squared minus B squared. Right. I think I got this right. Again, so you just remember, so this thing is going to be used to complete the solution to many integrals in which you need to use the trig substitution. I'm going to give you the complete solution to many questions I did not finish today. Okay, so again, the main thing today, we just concentrate on how to use a trig substitution to get rid of the radicals. Okay, so next time I will show you some tricks how to evaluate the rest of the integrals. Okay. For many questions, I'm going to complete the solution to the whole thing next time. For today, the assignment is going to be only asking you to use a trig substitution to get rid of the radicals. Okay. So good enough?
What, sir? Can you repeat it again, sir?
You say your question again? For today's assignments, the questions are in the nature that I only want you to use a trig substitution to get rid of the radicals. Okay, now the rest of the time we still have almost 30 minutes. I'm going to make some comments on the assignments. Okay, I haven't finalized the assignment yet, but the assignment questions are going to be something like I give you some integrals. The first part, okay, I give you some integrals. I will ask you to use a trig substitution to get rid of the radicals. For some questions we did not do in class, so maybe I'm going to make up some more questions. I hope you should be okay to handle this. And then other questions are going to be some volume questions. So like rotations and stuff. Okay, you still need to do more questions regarding the volume problem. At least we did new thing on Monday, the shell method. The shell method, right? The method of of cylindrical shells. So there will be some questions like this. Okay. So how about I'm going to make some comments one by one. Okay. Now look at question 4. Question 4 is going to be on the assignment.
So can I ask a question before
Sure.
we are talking about assignment?
Yeah, sure.
Actually, I'm a little bit confused about the last question we did.
Last question.
Yeah, the first one, secant theta is equal to 3, and in which we have to find the sine theta. Yeah, this one
Yeah, this one.
on the slide.
Okay,
Yeah.
sure. I'm going to open this. So what?
So I just wanna ask a question that if we know that perpendicular is equal to the base plus hypotenuse, the whole root. So in the first step you did 3 square minus 1 is equal to root of 8. So there should be plus 1 or not? Because perpendicular is equal to hypotenuse plus the base square, the whole thing square.
I think that's right.
Yep.
I think what I did is right. Secant of theta is 3. Cos of theta is 1/3. Cos of theta is 1/3, and the cos of theta is defined as adjacent over hypotenuse. So in the triangle, you need to make adjacent 1. You need to make the hypotenuse 3. So by that we mean you need to make the adjacent 1 and make the longest leg in the triangle 3. Right? And then if I use a question mark here, and then in the triangle it's going to be so something like 1 squared and then plus the question mark squared is equal to 3 squared. Right? So 3 squared is so question mark squared is equal to 3 squared and minus 1 squared, which is 8. So that makes sense?
Okay, I got it.
Yeah, 3 is the longest side. 1 is adjacent. The opposite is also not the longest. I think
Thank you, sir.
Sure, no problem. Okay, now we are going to make some comments on how about one by one. Okay, one by one. If you can recall the last assignment you did, I was trying to tell you why the formula for computing the volume of a sphere was true. If you had the answer right, the volume for question 1 on the last assignment, I haven't marked it. So did you get 3 over 4 times pi r cubed? I think r was not r, probably a cubed. The notation was a. That's the formula for computing the volume of a sphere, right? Using calculus, you see why that formula is true. I'm trying to say in the future you do not need to memorize. You just treat the sphere as the solid rotated upper half of the circle, and then you can get the volume using integral. Okay. Now my intention on this one is to show you why the formula of the volume of a cone is true. For question 4, I'm going to tell you the answer. The answer you are going to get is going to be V is equal to, you want to recall the volume of a cone. If you have a cone something like this, if the base radius is r, so maybe it's too small. If the base radius is r, if the height is h, so do you want to tell me what's the formula of the cone? I think it's 1/3 of the base area and then times height. Pi r squared is the circle at the base, and then h. That's the answer to this question 4. Okay. My intention on question 4 is to tell you why this question is true, why the formula is true. Okay, in high school or in junior high school, you're just told to memorize the formula. Now, after question 4, you're going to see why the formula is true. In the question, I did not replace r and h with any particular numbers. I will draw you a sketch. Now let's recall, in any case, the first thing you do is to draw a sketch. Okay. You draw a sketch. The sketch, I will tell you the sketch. Okay. I think the origin is here. The vertical axis is something like this. Again, here r and h are numbers. X and y are variables. Okay. So the graph of the equation y equals the graph of that equation is a line, and we restrict the line is from 0 to h. The setup is something like this. That's x coordinate of h. That's the height of that line segment. The height of that line segment. The setup is r. This line has the equation of y equals r over h, and then x. Okay, you see the slope is rise over run, right? It's kind of rise over run. Rise is r, run is h. I believe you can see it. Okay. That is the plane region. That is the plane region. Okay. If you want me to shade, I'm shading the plane region. Now I want you to rotate the plane region. Now I want you to rotate the plane region, the triangle, the red triangle, around x-axis. So do you see you have a cone? Rotate a triangle, a red triangle around one side. You have a cone, right? The cone has the base radius of r, the height of h. Yeah, that's why the answer you are going to get is that. Okay. Actually, for this question, it's easier to use the washer method. Okay. Now let's recall how to do the washer method. I will remind you some steps. Okay. So the first thing you do is to project the solid onto x-axis. You get the interval from 0 to 1, right? Sorry, it's not 0 to 1. It's from 0 to h. The second step in most cases is the hardest step. In the second step, we are trying to get the area of the cross section. You'll say something like this. For each x on the interval is from 0 to h, right? Imagine that x is here. X determines a little line segment. The same as before. You use the line on the plane region. You use the line, vertical line. You use the line perpendicular to x-axis to cut the plane region. You have a little line segment, and then you rotate that little line segment around x-axis. You have the cross section, which is a circle. Describe the cross section. Okay. The cross section perpendicular to x-axis is a circle. For a circle, you just need to get the radius, and then you can get the area of the cross section, right? I will stop here. After getting the radius, I will stop. So anybody want to tell me the radius? Again, so this point has x coordinate of x. What is the y coordinate? Point is on the line. The line, you know the equation of the line. What is the y coordinate of this point? Y coordinate is r over h and then times x, right? Now look at the point. Now look at this point. So does it make sense? The y coordinate of this point is the length of the line segment, which is the which is the radius of the circle, which is the radius of the cross section. Okay, I will stop here. After getting the radius, you know how to compute the area of the cross section, and then you integrate the area of all the cross sections from 0 to h. You have the volume.